Hi, this is my video number 14. My video number 14. So in this video, I'll talk on the arc length and as well as on the curvature. First we'll talk on the arc length. Arc length. Okay, so suppose that the curve has a vector equation given as RT as FT, GT and HT, where T between A and B, where F, G and H are continuous, as well as is a derivative where F prime, G prime and H prime are continuous. Then we have the arc length is given as integrate A to B magnitude of R dt. So this is the arc length of the curve from point A to B. The arc length of the curve from point A to B. So if you can draw this, just give you a bit idea what it is. Should be that. So let's say we have a length. This is your R. That's your R. RT. Okay, from T, from some point, let's say A to point B. So this length represents length from point A to point B along or through that curve. Okay, let's say example. I give you a quite simple example. If we were given, let's say, RT as cos T, sin T and T from a point 100 to point 102 pi. So if you differentiate this, differentiate that, we have this is negative sin T, cos T and 1, and find the magnitude of R prime. That gives us square root of sin squared plus cos squared plus 1. Sin squared, cos squared, this is 1, so that gives you square root of 2. And T you can take from here, because here this is for x. Alright, this is function for x or element component of x, component of y, this is component of z. So you can consider any of this, but this is much more easier. So you can see that z equal to t. So in our case, z from 0 to 2 pi. So which means t also from 0 to 2 pi. So we have t from 0 to 2 pi. Okay, so hope that you can follow me that. Therefore, the arc length from 0 to 2 pi, which is our t, the magnitude of those is square root of 2. So let me write those things. dt. So this is integrate 0 to 2 pi sec 2 dt, that gives you 2 sec 2 pi. Okay, so this is considered easy, but differentiating the arc length sometimes is quite difficult. Yeah, quite tedious. So let me give you another example. Let's say if you have r is given as, another example, r is given as t cubed plus t squared. T cubed t squared from t from 0 to 1. Yeah, find the arc length. Find the arc length of arc from 0 to 1. Yeah, from t 0 to 1. Alright, so yeah, first of all you need to differentiate those and find the magnitude. Yeah, differentiate those. You got 3 squared, 3t squared, 2t, and magnitude of those, this is a square root of 9t4 plus 4t squared. Okay, so integrating this is not easy. Yeah, integrating that is not easy. You need a lot of you need to do some substitution and so on and so forth. Okay, let's try that. So to find the arc length, we have arc length from 0 to 1, integrate from 0 to 1, arc prime t dt. This gives us integrate 0 to 1. I can put those 94 plus 4t squared to the half dt. Okay, it's if you can write this as something like square root 1 plus x squared. Yeah, so if you can do this, then we can use this substitution, tangent theta. Why? Because x squared, f squared, you got tangent theta, tangent squared theta, and then 1 plus tangent squared is, this is cos squared, secant squared, square root of secant squared give you secant theta. Give you secant theta. So let's do that. How can we make that terms into that? First thing, if you look at this, you can factor out 4. You can factor out 4. Let me write those things. You can factor out 40. Just look at inside there. So we have 4t squared plus 94. Just look at this thing. Okay. So this is equal to, you can take out 4t squared. You can take out those 4t squared, and then what left is 1 plus 9t4 over 4t squared. Correct? So you can cancel out that. Only 2, so we have half there. So you can put half here. I can put everything half here. Okay, and then here you have square root of those. So we got, this is 2t for 4t squared. You got 2t because of that half. And then inside here we have, you can write those things as a 1 plus, this is 3 over 2t, correct, squared, and half. So basically this is what we have, 2t integrate 1 plus 3 over 2t squared. So you have this form. Alright, then you can substitute those x. In this case, your x is 3 over 2t. So now, if you substitute into those our original integration, so what we have, those things, this is equal to, we integrate 0 to 1, we have 2t, integrate square root 1 over 3 over 2t squared dt. Okay, now we take this as a tangent theta, so substitute or let 3 over 2t, this equal to tangent theta. Then from there we have t is equal to 2 over 3 tangent theta. And dt, for that you have dt, we differentiate those dt, because when you substitute t, you also need to substitute dt. So dt d theta, this is equal to 3 over 2 secant squared theta d theta. Now what about the limits? Yeah, limits when t equal to 0 here, when t equal to 0, this is in the limit of integration. When t equal to 0, we have so tangent theta, so theta is equal to 0. When t equal to 1, so we have theta is inverse of, you can just bring in that side 3 over 2, so inverse 3 over 2. So now the limit of integration now, instead of t from 0 to 1, we have changed it to theta from 0 to tangent 3 over 2. Okay, so now change or substitute into that. So we have if you have 2t here, we have 2t, t is that, so means that we have 4 over 3 tangent theta for that. Okay, so let's write those things. So we have length is equal to integrate, now theta, you have t from 0 to 1, then we will show that theta change from 0 to inverse tangent of 3 over 2. So theta from 0 to tangent inverse 3 over 2. Then we have 2t here, so means we have 4 over 3 tangent theta. So we have 4 over 3 tangent theta. And then what else? So we have this 1 over square root everything here. So you have square root, or let me write that way, 1 plus tangent squared theta to the half. Okay, and we have dt, right? dt is given here. So we have 2 over 3 secant squared theta d theta. Now I think you can simplify this. So what we have now, this is equal to, this is 4 over 3, so we have 8 over 9, we can take out those things, 8 over 9. Then we integrate 0 to tangent 3 over 2. Now inside here we have this is tangent theta, alright, and this you have 1 plus tangent squared, this is secant squared, and this is secant squared, and square root, so you have secant theta. So you have secant theta, and for this we have secant squared theta. And note that d secant theta this is tangent theta sec theta d theta. So you can observe that inside here, so we have tangent theta secant theta d theta. So we have tangent theta secant theta d theta. That's one terms. So now those integral I can write 8/9 integrate 0 to tangent inverse 3/2. This is as a d secant theta, and what left is secant squared, so we have secant squared theta. Okay, tangent theta secant theta d theta is equal to d secant theta, so this is d secant theta. Now here you can just integrate with respect to theta. You know, secant theta as a variable. Now it's just the same thing as we integrate x squared dx. X is a variable, x is a variable there. So in this case, secant theta is a variable, that is a variable. So we have here, this is equal to 8/9. So we have secant three theta over 3. 0 to tangent 3/2. And then okay, so you can from here you can just evaluate those things, right? So whatever it is, I just leave it to you here. So 8/27 secant cube, substitute into there, so you have secant cube tangent -1 3/2. Okay, and minus secant cube 0. Of course this one is 0. Then right, is that 0? One yeah, that's a 0. Okay, so that's the answer. Now let's consider, I gave you this as an exercise to you. RT is t squared t cube, where t from 1 to 2, and number 2 we have RT is equal to EU, here is RU, not T, E2U, E3U, where U from 0 to ln 2. Okay, try that as an exercise. You know, the tedious part is how to integrate the magnitude of R prime. So you need to use substitution and so on. You can refer to the calculus book, yeah, on the evaluating the integral, especially involve trigonometric function and inverse trigonometric function as well. Okay, so I have done for that. Let's go to our next chapter or next topic, that curvature. Yeah. So what is curvature? Okay, so generally speaking is that you can consider, let me just describe to you, right? You can consider a curve. Let me say there's our curve, say like that. So we can see from as t change from some point here to this point there. Okay, so let's say from this point to this point. Okay, so there is a difference rate of change. So make it, you know, it's not uniformly curved. Here you have the change of direction is a little bit small as compared to there. So you can see this here like that, and then it's getting sharper and sharper, and then back to a little bit there. So that's an example of what we call this curvature. So basically the curvature is rate of change of those things. Okay, it's keep on changing, and here at this part here is getting quite sharp corner there. Okay, so to describe this thing wordly, so I would say, let's say I have a tangent line here. Okay, so let's draw those tangent line. That, so let's consider this as a line L, and at this we call it a point P. Okay, and this is the what we call the what we call that, those things. I lost that word. Can I say Malay? It's a sasaran. You know sasaran in English, what is it? I cannot recall this thing, right? And then we take this angle as a theta, and this as a y, you know, this as a considers as x, and okay, now so we define this thing. So with that we can define. So basically you can see as this point P change. Let's say from here, let's say this is a point P, the changing point, keep on changing. You can see the distance between those point to P with respect to S. So it's getting bigger and bigger and bigger. And if at each of these points we plot, or we draw the tangent line here, we draw the tangent line, and so on. So you can see the angle theta change as S change. Okay, the angle theta change as S change. Tangent theta is line angle to the tangent line. So you can see if the point here, the theta is here, quite small. If the point there, theta is here, getting bigger and bigger and bigger. So you can see at this point, for example, if you plot the tangent line, so this is our theta. Okay, so let us give definition. The curvature we denote as kappa of a curve y of fx at point P is given as, now in this case this is our real valued function. Later on we'll go to the vector valued function. For the real valued function here, the curvature kappa is given as the s over d theta over ds. So wordly we can say this is the rate of change of theta with respect to s. So I would say theta is a function of s. Okay, so what does it measure actually? So the curvature at point P measure how quickly the curve change direction at that point. Okay, I have explained what we mean by change direction. If you look at here, if you put, I put my pen here like this, so you can see this. Here is quite slow, and then the change is quite fast here, and quite big there. So that means a change of direction. Okay, so now how to evaluate this? Now, how can we calculate or evaluate the stress, the curvature? So we have a theorem for that. You have a theorem. If y is a function of fx is twice differentiable, function. Yeah, twice differentiable here means you can find y prime and you can find y double prime. Yeah, so that means twice differentiable. Then the curvature for y fx is given as kappa d theta ds. This is by definition. This is given as y double prime over 1 plus y prime squared 3/2. Okay, so that's the this is the definition of curvature. Then this is how do we calculate the curvature. Now, how to prove this, or how to obtain that formula? Let us prove this. Now, if you look at this figure, and I transform those triangle here, where I consider a very small movement from some point here to point P. All right, so we have look like very small angle there, very small triangle. So this small triangle, let's denote this as a dx, this is as dy, and we denote this as a ds. Okay, so from there it is pretty obvious. You can use what we call that it just won't come up in my mind. We use the okay, you can find those things. We have a ds squared, this is equal to dx squared plus dy squared. Okay, and then I can divide this thing by dx squared. Yeah, I can divide those things by dx squared. What we have then, ds dx squared, this is square root 1 plus dy over dx squared. Correct? So I can have ds, I can write ds dx, this is square root 1 plus dy dx. Dy dx I can write as a y prime squared. Okay, now also from that figure, if you consider this as a theta, yeah, so we have tangent theta, this is dy over dx, dy over dx, and dy over dx, this is y prime. Okay, so if we have here y prime, so dy dx, so y prime, this is dy dx, this is tangent theta. Alright, and I can write y double prime, this is dy dx, d2y dx squared, d2y dx squared, this is equal to second second squared theta d theta. And second squared theta, this is the 1 plus tangent squared. Yeah. So this is actually equal to, I can write this is as a tangent squared theta d theta. Okay, and tangent squared theta, if you can use this, where is it? Tangent theta is dy dx y prime. Okay, so tangent squared theta means y prime squared. So I can write this here as a 1 plus y prime squared d theta. Yeah. Okay, so this is d theta, supposed to be d theta dx, d theta dx, that's what we want. And this is d theta dx, right? Oh, sorry, without that. Okay, that. So I can write, therefore I can write d theta dx, we can write d theta dx, this is, oh, where is it? Yeah. So d theta dx is, we have y double prime over 1 plus y prime squared. Okay, so we want to find d theta ds here. Okay, we want to find d theta ds by definition. So therefore we have our kappa, which is d theta ds. So let's evaluate d theta ds first. So d theta ds, this is so we have d theta dx. So let's use the d theta dx. This is d theta ds dx. So we can find d theta ds then. D theta ds, this is given as d theta dx ds. Okay, so this equal to, so d theta dx, we have d theta dx here, and dx ds, I think we have you evaluate ds dx. Yeah, we already obtained the ds dx, or ds ds, we just inverse those things. So we have ds dx, we have this from there, and let me write this thing, ds dx is given as, or we evaluate this 1 prime squared. Okay, now if you substitute into that, so we have, this is d theta dx, so we have y double prime over 1 plus y prime squared, that, and dx ds is 1 over 1 plus 1 prime squared to the half. That gives you y double prime over 1 plus y prime squared 3 over 2. So for the kappa, so therefore kappa is magnitude of that, so that gives you magnitude of y double prime over 1 plus y prime squared 3 over 2. Okay, because here you have squared, so it's always positive, so we don't bother on the modulus sign. Okay, so that's the curvature for the real valued function. Now let's look at the curvature for the vector valued function. We have a theorem. If RT is given as f of t, g of t is a twice differentiable vector valued function, or vector function is twice differentiable vector function, then curvature kappa is given as x dot y double dot minus x double dot y dot divided by, we have x dot squared plus y dot squared 3 over 2, where x dot is dx dt and y dot is dy dt. Okay, let's try to prove this. I wish I could just leave it to you to do it. It's not that difficult because we already have the formula. So what you need to do is from the formula for the kappa for the real function, you just need to find what is double prime in terms of t, what is y prime in terms of t, then you can just substitute into that, then you can solve. So let's try. Let me guide you halfway. I'm not going to do all, I hope. Let's see. So we have from there, from the given theorem there, alright, so this is component for x, this is component for y. So I can write those, let x equal to ft, so means x is a function of t and y is a function of g. Okay, so from there I can find dx dt. Of course, the dt is given as f prime t. I can find dy dt as a g prime t, and I denote this dx dt given that dx dt is as x dot, and dy dt this is y dot. So therefore you can find what y prime is in our formula. That is, in our formula here we need y prime and we need y double prime, so you can find what y prime and y double prime. So we try that. So y prime, which is dy dx, you can just use a chain rule here. So we have dy dt dt dx. So that gives you dy dt is y dot, and dt dx is 1 over x dot, so you have x dot over y dot. Okay, from there you need to find y double prime. Y double prime. So y double prime, we differentiate d dx dy dx, correct? Which means I have to differentiate this which means I have to differentiate this. So d dx y dot over x dot. Okay, so to differentiate this, we have x dot d dx y dot minus y dot d dx x dot over x dot squared. Okay, now from there we have x dot there, x dot. Differentiate that x y dot with respect to x, so you're going to have y double dot over x dot. Okay, how to get from here to here? I want you to find out those things. It's not difficult. Just use chain rule, and it's from this part here. Just use that, and then minus y dot. We have this. This is x dot. So we have x double dot over x dot. And here we have x dot squared, x dot squared, and then you can simplify this. I think, yep, that's cancelled out with that. So what left is that y double dot. You can take out those, so we have x dot y double dot minus y dot x double dot 1 over, so denominator we have 1, you have 2, so we have x dot cube. Okay, now we have y double prime, we have y prime. What you need to do is just substitute into our formula y double prime over 1 plus y prime squared 3 over 2. Then if you do this, substitute everything there, you get that. Okay, let me end up with a quite simple example. Example, find curvature kappa for y equal to x cubed at x equal to 2. Yeah, you just use the formula kappa is y double prime, because this is the a real function, so we use the real function over 1 plus y prime squared 3 over 2. Okay, so we have from there y prime, this is 3x squared, y double prime 6x. Correct. So if you use this, so this gives us 6 magnitude of x. We have 1 minus y prime squared, so 9x to the 4, and we have 3 over 2. Okay, of course, in evaluating those things, you need to evaluate those. You need to take into consideration the absolute symbol there, so that give you minus 6x over 1 plus 9x4 3 over 2 4x negative, and you have 6x over 1 plus 9x squared 3 over 2 4x positive. Okay, and then you just need to evaluate x equal to 2. X equal to 2 is, you can use that one, but somehow it still give you a same answer because we have absolute value there. Okay, now if I give you another example, the how to evaluate, let's say if you were given a vector function with t and t cube at t equal to so we have x equal to 2, let's say equal to 2 as well. Okay, so if you look at the given component of R, so you can write x equal to t, y equal to t cube. Alright, so basically this is just the equation y equal to x cube. So now it's exactly the same equation. You should get the same answer. But in this case, I want you to evaluate using the curvature for the vector function. You can have another one. Find k for x equal t plus cos t and y equal to 1 minus sin t, and at t equal to pi over 4. Now up to now we discusses the curvature for plane that involve x prime and y prime, and so we don't have z at the moment. So later on we will discuss on the curvature on the space. Alright, now with that, let me conclude what I have done. So at the beginning, we will begin with the arc length. Alright, the arc length, and I gave you an example. One is quite easy, one is quite tedious to find the integral. And then I give the definition of what is curvature, and I give quite explanation on that, and the how to evaluate the curvature for the real function as well as for the vector function in 2 dimension at the moment. Alright, so with that, I thank you. We'll meet again in the next video. Bye.